So now we're moving on to a problem that is going to be harder. Same type of stuff, but it's just going to have a few extra steps in it. So here are the elementary steps for this reaction. This is going to be, we're going to call this one step 1. We're going to call this one step 2. And this time we're just being told right off the bat, K2, this is our slow step. So we don't have to try to compare the values of K. Now notice something different about this one. Elementary step 1 is in equilibrium. And so we have two K values for this elementary step 1. We have a forward and a backwards rate. And we're calling them, this is standard notation, we're calling the forward reaction K1 and the backward reaction K-1. And that's just always how it is. So if K2 was also in equilibrium, it's not, but if it was, we would have a K2 and a K-2 for its back reaction. And you guys are smart enough to know that there isn't technically a forward or backward reaction in equilibrium. So when we say forward, we mean as it is written. So the way that the reaction is being presented to us, this is the forward reaction as it is written, and this is the reverse reaction as it is written. So the first thing that we're going to do is come up with our overall equation, and that is going to be from combining the two equations together. And it's kind of tricky with equilibrium. So when we're doing this with one of the reactions that is in equilibrium, we're going with as it has written. So that means that we are calling these guys our reactants, combining them with these reactants right here, and we're calling these guys our products, combining them with these products right here. So our overall reaction, the reactants are H2 plus 2NO, that's from reaction number 1, plus another H2 and an N2O, and the products of this overall reaction are N2O plus H2O, that's from reaction number 1, plus N2 plus another H2O. Another H2O. And now remember with this, once we get our overall equation, whether we're talking about combining redox reactions or this type of thing, the next thing that we have to do is simplify, look for things that we can eliminate. We have H2 on the left, but we don't have any H2 on the right. We have NO on the left, but no NO on the right. We have N2O on the left and on the right. So that's going to be the thing that we simplify. And then remember, the thing that we get rid of, that is our intermediate. So let's make a note of that because that's probably going to come back to us later. We're probably eventually going to be asked what the intermediate is. Our intermediate is N2O. And remember, again, the intermediate is coming from the elementary steps. It's produced in one of the elementary steps and then used as a reactant in the next elementary step or in a later step. So now we're going to move on to writing our rate laws for the first step in the forward direction. So elementary step number 1 in the forward direction. We're going to call that rate 1. We're going to call that K1, and it is equal to the concentrations of the reactants when we're looking at the forward direction. So H2 and NO, and remember that the stoichiometry, the stoichiometric coefficients in the elementary steps are the exponents in the rate law. Now we're going to do the same thing for the reverse reaction of elementary step number 1. So for the reaction that goes from right to left, we're going to call that rate -1 because it's the reverse reaction. Its constant is going to be K-1. And when we're going from right to left, our reactants are N2O and H2O. Now we have one more rate law, and that's for elementary step number 2. It only goes from left to right, so we don't have a minus. This is rate 2 is equal to K2 times the reactants H2 and N2O. Oh, and so here we go. I told you it was going to eventually ask, what are the intermediates? We decided that the intermediate was N2O. So now we want to, step 6, write the overall rate law of the reaction. In the previous problem, we learned that the overall rate law is going to come from the rate law of the slow step. So let's go back up and figure out which one is our slow step. Our slow step is step number 2. So the rate law for elementary step number 2 is going to give us, it's going to lead us to the rate law for the overall reaction. So here is our rate law for step 2, the slow step. Rewrite the rate law of the slow step using rate, not rate 2. Rate equals, leave the subscript on our rate constant, K2, H2, N2O. Awesome. Our overall rate law, which we just came up with, will contain an intermediate. So our intermediate, N2O, is here in the overall rate law. And remember, I told you that's not okay because that's not a measurable species or a controllable species. We can't dictate the molarity of the N2O that's in this reaction. So we're not going to be allowed to leave it in this term in the rate law, but we will be able to get rid of it. So here is how we're going to go about getting rid of it. Step 1 is in equilibrium, and that means, you've probably forgotten this because it's been a while, but when you are in equilibrium, the definition of equilibrium, the rate of the forward reaction is equal to the rate of the backwards reaction. That is the definition of equilibrium. So when we are in equilibrium, we have equal rates, and we have equal rate constants. So that tells us let's scroll back up and look at it again, for this step 1, which exists in equilibrium, we can say that the rate of the forward reaction is equal to the rate of the back reaction. And we can also say that the rate constant of the forward reaction is equal to the rate constant of the back reaction. But we don't need that yet. What we do want to do now is use this equality right here to combine the 2 rate laws for elementary step 1 into one beautiful mathematical equation. So let's get those 2 rate laws. Rate 1 is K1 something something. We're going to have to scroll back up. And rate -1 is K-1. Let's go see what those terms are. For K1, it is H2NO squared, H2NO squared. So all we're doing right now is just copying them. And then for K-1, it's N2O, H2O. N2O, H2O. So now we have them where we can see them. So what we want to do is combine the 2 rate laws into one mathematical expression. We're going to be using this equality here. Instead of writing rate 1, we're going to write this term. And instead of writing rate -1, we're going to write this term. So we're going to get K1H2NO squared is equal to K-1 N2O H2O. And the last thing that we're being asked to do here, rearrange this expression to isolate the intermediate that you identified in problem 5. Our intermediate, N2O. We want to isolate the N2O intermediate, this guy right here. So we're going to do that algebraically. We're going to move K-1 to the left side of the equation, and we're going to move H2O to the left side of the equation. What the heck are we doing? What did we just do? What we did was define the concentration of N2O, an intermediate, in terms of measurable things, H2, NO, and H2O, which are all species that are either reactants or products, things that we can measure. So we have rewritten an unmeasurable quantity in terms of measurable quantities. That's very powerful. Next, use the expression for the intermediate that you derived in problem 7. So this is the expression for the intermediate. Plug it into the overall rate law. The overall rate law, this is our overall rate law. Rate equals K2, H2, N2O. Rate equals K2, H2, N2O. Now we are going to plug this term for N2O into this part of the equation. So we are going to get rate equals K2, H2, K1, H2, NO, oh, I forgot my bracket, NO squared over K negative 1 H2O. And clearly we can clean that up. We can make it look a little bit better. Let's see, I'm going to put it down here. We'll clean it up down here. So we can go, let's put all the K's together. K2, K1, H2 is squared, NO is squared over K negative 1 H2O. Now, typically at the end of this, we want to simplify the rate law by rewriting all of these individual rate constants into just one massive rate constant. So instead of writing it in this form, we will say rate equals K H2 squared NO squared over H2O. And then on the side, we'll say K, this term that we introduced right here, K is in place of K2, K1 over K minus 1. K2, K1 over K minus 1. So both of these parts together are the answer. We need, not only do we need the rate law, but we also need an explanation of what is meant by the rate constant K.